So in this example, I would like to apply the central finite difference method to solve a one-dimension heat conduction problem. And among the boundary conditions, I have one phase that's fully isolated. The second phase of the one-dimension bar is exposed to a convection stream with a given infinity temperature and convection heat transfer coefficient. In addition, I would like to have a heat source embedded into that one-dimension bar. So the schematic of the problem or the design is a bar has a length of 0.6 meter. The left face of the bar is fully insulated, which means that its maximum temperature is expected in this side, and which means that the temperature gradient is also expected to be 0. So mathematical translation of the insulated surface is T is max, and also partial T by partial X should equal to 0. And if we measure our X direction from here, so this should be valid at X equal 0. Then the second end of that one-dimension bar is exposed to a T infinity stream, that's 20 degrees C, and H convection heat transfer coefficient of a value 10 watt per meter square Kelvin. And the bar, the one-dimension bar, has a heat source of 10 to the 4th watt per meter cubed. Now find the temperature distribution along the bar using the same delta X that we used before, that equal 0.1 meter. So again, this is my problem statement. This is my design. Now, what's the governing equation? What's the model that we will apply? It's still the heat diffusion equation simplified to these two terms. It's one-dimension problem. X and Y and Z are gone, and it's a steady-state problem. So the right-hand side of the equation is gone, the energy stored, and what remains is just the second gradient of temperature relative to X and the heat source. And remember, K is supposed to be in this side, so we divide by K. That's why K is coming under the Q dot. So that's my model, right? Then we did the simplification. Now we need to do the grid and mesh as part of the discretization problem. So my mesh or my grid, again, the problem is requesting delta X to be 0.1 meter, which means that I will break down my bar into 1, 2, 3, 4, 5, 6 elements. I will mark the location of the node. I will follow the previous example. So I'm going to call that node 1. This is node 2, node 3, node 4, and node 5. And the interface here, I'm going to give that node 0. It's still unknown temperature point here. Keep in mind, energy balance equation also is valid, right? Just keep that as a second equation here. Energy in plus energy generated equal to energy out plus energy stored. Solving steady state, eliminate the stored energy part. When we come to the transient part, we will add that term. And again, we are experiencing the energy balance method, which means that we assume all the energies are coming into your control element. So E out would be 0. So this would be simply the final form of the energy balance equation if you are interested to use. Now, let's see the discretization here. So I will go with node number 5. Again, remember, central finite difference method, the second derivative of the temperature at node I can be expressed as Ti plus 1 minus 2 Ti plus Ti minus 1 divided by delta X squared, right? If you substitute into this equation, your governing equation will be simply partial 2T by partial X squared. This will be substituted by Ti plus 1 minus 2Ti plus Ti minus I minus 1. This is multiplied by 1 over delta X squared. Then I will add the term Q dot over K is equal to 0, multiplied by delta X squared, both sides of the equation. So I will have Ti plus 1 minus 2Ti plus Ti minus 1 plus Q dot delta X squared divided by K equal to 0. We can set aside and get actually the calculation of that term. is going to be a constant term. It's not going to be changed with the location of the node. So let's calculate that as a constant value, 10 to the fourth times 0.1 squared divided by K. K of that bar was given previously by 10 watt per meter square Kelvin. So that's actually 10. This will give me 0.01. It will give me 100 out of this multiplication divided by 10. So that value is 10. And this is very similar to what we got if you visit our previous example when the heat source was included before. So this equation will be simply Ti plus 1 minus 2 Ti plus Ti minus 1 plus 10 equal to 0. So now let's apply this equation here for node number 5. Remember, node number 5 is surrounded by a full control element, right? Which if you are using the energy balance method, it's going to be Q dot time the volume of that phase here. If you are using the energy balance method, same apply for node 4, 3, 2, and 1. But when it comes to node number 0, we will have half of that control element. So just pay attention if you decided to go the route of the energy balance method. We will mix that in this problem when it comes to node number 0. So for node number 5, I would have Ti plus 1, which is T4, minus T2 of T5, plus T to the left. Oh, now we are getting different situation here. Okay, so let's start with node number 4. So it's T3 minus 2 of T4 plus T5 plus 10 equals 0. So that's clear. When I applied the equation to node number 5, I exposed to a temperature gradient to the left, right? Which is the isolated surface. So I couldn't find a free node to add to the equation. So for node number 4, it's easy. I have a node to the right, I have node to the left. 2 of the node, the base point plus 10 equals 0. So that's the same apply for node number 3. So I would have T2 minus 2, T3 plus T4 plus 10 equal 0. Then for node number 2, I will have T1 minus T2 of T2 plus T3 plus 10 equal 0. Then when I go for node number 1, it's still, the equation is still valid. It's going to be T node minus 2 T1 plus T2 plus 10 equal 0. So now we got 4 equation and multiple unknowns here. So we still have 2 nodes or 2 sides to apply. We still need node number 5 with the left boundary condition. Let's see how we're going to do that. And then node number 0. Let's figure out how to deal with these 2 specific boundary conditions here. Usually the nodes near the boundaries is the one that need a little bit of more work to be able to extract a nodal equation or an additional algebraic equation to fit into your system of linear equations. So let's see how we're going to deal with node 0 and node 5. So for node 5, if I apply this equation, I'm going to need a node to the right, a node to the left. We know that at the insulated surface, the temperature will be max, which means that we should have a new node added to the interface here, and we're going to call that T6. If that's the case, I should add node 5 as well into that system of equations by saying that it's going to be T4 minus 2, T5 plus T6 plus 10 equals 0. But now I have additional unknown, which means that I need to apply the discretized equation for node number 6 and node number 0. So I end up having 7 nodes, 1, 2, 3, 4, 5, 6, 7 nodes. I have now 5 equations. Now I need to get into node 6 and node 0 to get the 2 additional linear equations. So let's start with one of them. I will start with node number 6 and see how we can extract that equation. So let me draw actually the node number 6 in a larger scale here. So that's node number 6. This is the insulated face. Then I have node number 5 is here. Now let's actually draw the control element surrounding node number 6. I should draw a square of the same dimension of delta x side length. That's the original delta x. This is my 0.1, right? So I should come around point number 6. I'm going to draw a square of a width delta x. Half of it will be in the middle of nowhere. I cannot have that. It's not part of the domain. So I'm going to have this as delta x over 2. And this is where the domain, whereas the heat generation is actually applied. Now let's look to the energy now. According to the energy balance method, all the energy has to be coming in. So I'm assuming that I'm going to receive part of that Q because of the high temperature or the temperature difference between node 5 and 6. But because of that face is fully insulated, there is no heat in or out, right? According to the energy balance, I should have like Q in, but this will be 0 because the surface is not allowing to receive any energy. So now if I apply the energy balance equation, energy in plus energy generated will equal 0. Now energy in will be only Q1 plus energy generated will be Q dot times the volume of the element, which is going to be A times delta x over 2. That should equal 0. This Q is coming by conduction, so it's going to be K times A T5 minus T6 divided by delta x, the distance between the nodes, plus Q dot A delta x over 2 equals 0. A will cancel out. I will multiply the equation by delta x over K. I will have T5 minus T6 plus Q dot delta x squared over 2K equal 0. Q dot delta x squared over K give me 10. Now I'm dividing by 2. So the equation will be T5 minus T6 plus 5 is equal to 0. And this is the equation for node 6. So what's about node 0, right? So node 0 now I have the right side of the problem, the right boundary condition. This is node 0. Then I should have node 1 in here. Now, if you draw the control element, you should have that line here over a distance here that's delta x over 2. The overall distance of between the two nodes is delta x. Now, according to the system here, I have Q dot inside that half control element. Then I'm exposed to a convection here. So I have T infinity and I have H, right? And we have the values. T infinity is 20 degrees C and H is given by 10 watt per meter square Kelvin. Now there is a Q coming in here. That's Q1. There's Q coming in here. That's Q2. If I would like to apply the energy balance method, I should have E dot in plus E dot generated equal to E dot out plus E dot stored. This is 0 for steady state condition. This is against the general assumption of the energy balance method. So I will have here Q1 plus Q2, adding up these two values. This is energy in plus energy generated will be Q dot times the volume of the control element. And the volume of the control element will be actually A times delta x over 2. Then this is equal 0. Q1 is coming by conduction, so it's going to be Ka T1 minus T node divided by delta x, plus Q2 is coming by convection, is going to be HA T infinity minus T node, right? So I'm going to distribute that. Here is T infinity, and there is HA T node. So this is the convection term, plus Q dot A delta x over 2 equals 0. Multiply the equation by delta x over Ka, or simply first cancel the A out. Then you multiply by delta x over K. I will have T1 minus T node plus H delta x over K T infinity minus H delta x over K T node plus Q dot delta x square over 2K. Remember, we did calculate Q dot delta x square over K. This value is 10. So this term here will be simply 5. then h delta x over k, h delta x over k, h is actually 20, is 10, delta x is 0.1, and k is 10. So I end up having this is 0.1. And T infinity is given by 20 degrees C. So T1 minus T node plus h delta x over k, which is 0.1 times T infinity, which is 20, minus 0.1 T node plus 5 equal 0. So you'll find yourself that T1 minus 1.1 T node plus 5 plus 2, that's going to be 7 equals 0. And this is the very similar equation that we got in the previous example that we didn't have the isolated tip, the one that we just have a Dirichlet boundary condition on the left side, then we have convection on the right-hand side. Now you have the how many equations we have? We have 1, 2, 3, 4, 5, and 6 equations for actually 7 equations. Here's 1, 2, 3, 4, 5, and there is one for node number 6, and we have one for node number 7. We have 7 nodes from 0 to 6. I will simply go and solve that by iterative method. You can use any one of the iterative methods. You can watch that in the previous recording, or you can simply go into the MATLAB and use a matrix. I simply use the matrix, and I got the following results. I got T node equals 620. I got T1. So after you solve, you will get T node equal 620, T1 equal 670. I got T2 720. I got T3 755. I got T4 equal to 780. Then I got T5 equals 795. And T6 is equal actually 800. So let's recall what we did before. In the first example, we had that one dimension bar with 100 degree here, a 20 degree here, right? And we were able to see that the temperature distribution was very simple, linear, right? If this is my x-axis, and this is the temperature, there was a linear change in the temperature. And if you recall the values, it's going very consistent with that slope of that line. Then in the second case, or the previous case, we had the bar that's, yeah, so we had that bar here. We exposed that guy to a convection. And this was 100 degree. So in this case, we still get a linear distribution, but the difference was a different slope, right? There was a different slope, but it was still linear distribution. And in case 3, we added heat generation to that bar. So this was actually the first example that we did. This was example 2, and this was example 3. It's exposed to convection at one end. We kept that 100 degree, but we added heat generation into this body here. And if you recall the values, we got actually the temperature distribution looks like that. There was a kind of a parabola, but peaked in the somewhere in the middle. I think the peak was actually at node 0, 1, 2, 3. I think node 3. This was at node 3 with a value of 195 compared to something like 85 degree for node number 3. Now, for the current case that we are doing here, we isolated the left boundary. It's isolated tip case, so that was isolated. That's case 4. And we still have this exposed to T infinity and H. We get the same. You realize that the maximum temperature is actually at node 6. We are getting a parabola looks like this. It peaks up here, then it's actually goes slowly down, 800, 795, 780, all the way until it reaches 620 at the surface. Then it's exposed to that convection, whereas the convection is. Okay, on convection, it's simply a gradual decrease until you go far away from the wall and the impact of the wall demolish, and you just get steady temperature value, which is the ambient temperature. So that's T infinity here. That's T infinity here. That's T infinity here. So this is temperature distribution based on each case. And by the way, for all these cases, the analytical solution is available. You can solve Laplace equation in one dimension without heat generation in the first two cases, just different boundary condition, or with heat generation. This heat generation case with different boundary condition here. This is the case where the isolated boundary is present, and this is where the maximum temperature will come. So you can do the analytical solution for all these cases. So that concludes here the most cases that we may get exposed to. Either we are using the finite difference method, or you go for finite element, or you go for finite volume. This is what we looks like. This is the most cases that we're going to expose to most of the time. But what's going to happen is we're going to take the level of that one dimension problem into maybe multi-dimension. Maximum, we're going to go 2 dimension. We will not go 3 dimensions. It's going to be complicated mathematically, and we can do that computationally using codes. But at least to practice that, we will elevate the level of the challenge to the 2-dimension problem. So let's see how we're going to do that in our next slide here.